Math 287, Quest to College. I'm Joe Vasta. This is Review 2. Let's work on some problems. A lot of these problems I do at the beginning will come right from 4.11, which is the review. And look what we have here. We have, is S a subspace of V? So V is R2 and S looks like this. There's actually a few ways of doing these problems, and I'm going to show you a few approaches. Really what you need to know is yes or no. I mean, that's what you want to decide. So one way of doing this problem is to go like this, that we could solve for y on that. So y equals x squared. So we can write an element in S. This is a subset. We're seeing if it's a subspace, which is a vector space within a vector space. So we can write an element like this. Element of S looks like x squared. Okay, can we break any of the closure axioms? Addition, is it closed under vector addition? Is it closed under scalar multiplication? Let's just go ahead and pick something that lives in that set. Okay, and set S, which would be maybe 3, 9. So could I break this by, maybe multiplying it by a number? To be in this party circle, to be in set S, your first coordinate could be whatever it wants to be, but the second coordinate has to be the first coordinate squared. So perhaps I go 2 times that. What do I end up getting? 6, 18. So this guy right here could be whatever, but this would have to be 36 if that was 6. So this 618 is not in the party circle. So the answer is no. Another way of verifying this would be all the vectors in R2, where if you put their tail on the origin, the head would have to go on that parabola. So you can easily see something like this. Here's a vector that looks like this. I don't know where it's going on there, but if you multiplied it by 2, it would not be on that parabola anymore. And so we can come to the conclusion of no using a picture as well. Let's go ahead and do another problem. Oh, the very first thing we should have done is we should have seen if 0, 0 was in that set, and it was. So that's how I'll start this one. Is S a subspace of V? Does 0, 0 belong in S? And it does, because you have 0 and 0 cubed. Okay. So this is kind of like the last problem. I'm going to pick an element like 2, 8. 2, 8. Okay. To be in the party circle, your first coordinate could be whatever it wants to be. The second coordinate has to be the first coordinate cubed. So why don't we go ahead and multiply this thing by like 3. So this gives me 6, 24. Well, we know 6 cubed is not 24. This guy is not in the party circle. So the answer to this problem is no. We could have drawn the graph of this, which is really y equals x cubed, and we could have done that as well. I also believe the axiom 1 fails on both of these problems. So let's do another problem. Vector spaces 2 by 2 matrices. S is A, B, C, D, where A plus B equals C, and C plus D equals B. So in order to be in the party circle, the sum of the first row has to equal that element down there, and the sum of the second row has to equal this element B up there. So what we do is we think about it, we go, let's see if 0, 0, 0, 0, which is the 0 vector, is in this party circle. And it is, because 0 plus 0, the top row equals that 0 there, and the bottom row equals that 0 right there. So we can't get out of it that easily. So let's check our axioms, unless we can think of an example that breaks this. So I'm going to go ahead and put A, B, C, D there. And I'm going to add it to another matrix in the party circle. So E, F, G, H. Okay, so we do have A plus B equals C, and C plus D equals B. And then over here we do have E plus F equals G, and G plus H equals F. Okay, because it's in the party circle as well. So let's see what we get here. We end up getting A plus E, B plus F, C plus G, D plus H. So does the first row add up to C plus G? Well, let's see. Does A plus E plus B plus F equal C plus G? So we'll put a question mark over that. Well, we know that A plus B equals C. We also know that E plus F equals G. So yes, we do have the first row adding up to C plus G. It is equal. Let's go ahead and check to see if the bottom row adds up to the top right element. Does C plus G plus D plus H equal the top right element, which is B plus F? Well, we know that C plus D equals B, because this guy's in the party circle. And we also know that G plus H equals F. This was a question mark as well, and so this is yes. So when you add two creatures from the party circle together, you get a creature that is in the party circle. Axiom 2 says scalar multiplication, R times A, B, C, D, will also be in the party circle. Let's check this out and see what happens. We have RA, RB, RC, RD. Okay, well let's check. Does the sum of the first row equal the bottom left entry? Well, if you divide everything by R, well, if R is 0, you won't want to do that, and it will say that equals that. But if R is not 0, so if R is 0, it works. If R is not 0, you can divide everything by R, and you get A plus B equals C, which is good. So that one's good. And C plus D equals B. So does the sum of the bottom row equal the top right entry? Does RC plus RD, does that equal RB? Well, if R is 0, yes, and if R is not 0, divide by R on both sides of the equation, you'll get C plus D equals B. And so that's a yes as well. So we have yes. This guy's in the party circle. Is S a subspace of V? The answer is yes. Let's go ahead and do some more examples. This one I just made up here. So we're going to do some more examples from the review, which is 4.11. So this is 4.11. And so I've kind of modified the instructions to ask a little more, so we could actually practice some other skills that we'll need to know. So I'm going to give you a vector space V and a subspace. And now I'm giving you, no, it's not a subspace. I'm giving you a set of vectors. Okay, so I'm giving you a vector space V, and now S is going to be a set of vectors within that vector space. Does S span V? Okay. Is the set independent or dependent? So that's where the book stops. But there's other questions within the homework and that might be on the test or will be on the test that you need to know. If S is dependent, then find a relationship. If S is dependent, then find an independent set of vectors that spans the same subspace of V as that spanned by S. So basically part D says kick out the dead weight. And then E is S a basis for V. And we could probably answer that like right after we answer A and B. So let's go ahead and look at our first example. Our first example is number 24. Now you might pause this and see if you can do this problem on your own. Okay, so let's talk about this. Does S span V? Okay, so I'm going to move this off to the side, and I'll just verbally say these from time to time. Well, here's the deal. In order to span R3, you need how many vectors? You need 3 vectors. So does S span V? The answer to that question is no. Part B. Is this set independent or dependent? Now to check for that, you would go constant times that one plus constant times that one. So set up all linear combinations and set it equal to 0, 0, 0. And then see if you have any dead weight. But if you only have 2 vectors, you only have to check to see if they are scalar multiples of each other. Are these guys scalar multiples of each other? The answer is no, they are not. So you do not have dead weight, which would mean that these guys are independent. Now we'll do another one where there's more than 2, and then if you don't see scalar multiples, you can't jump to the conclusion of independence, because there could be a dependency relationship. Part C and D, they were saying, well, if it's dependent and do this, find a relationship, well, it's independent, so there's no dependency relationship. And then part D says kick out all the dead weight. Well, there is no dead weight, not applicable. And then part E, which we could have answered right off the bat, is S a basis for V. Well, it doesn't even span R3, so no. Okay. A basis is a minimal spanning set. Let's go ahead and do problem number 25. So we'll just do a few consecutive problems here, and then we'll turn our attention to other things. Our vector space is R3, and we have these 3 vectors. And they are asking questions. The first one, does S span V? Is S a basis? That was the last question. Independent, dependent. So we have all these questions. What I do when I have more than 2 is I set up all linear combinations of these and set them equal to 0, 0, 0, the 0 vector. So that's what I'm going to do. C1, 6, negative 3, 2, plus C2, 1, 1, 1, plus C3, 1, negative 8, negative 1. This equals 0, 0, 0. Okay, of course this gives us 3 equations and 3 unknowns. So I have 6 C1 plus C2 plus C3. This equals 0. And then the second component's negative 3C1 plus C2 minus 8C3 equals 0. And then the third components, we have 2C1, then we have plus C2, minus C3 equals 0. Okay, the next thing I'm going to do is I'm going to set up the augmented matrix. 6, negative 3, 2, 1, 1, 1, 1, negative 8, negative 1. Here's my equal sign. Here's 0, 0, 0. Okay. Well, what is the next step on this? The next step is doing row operations, which I have not done. I'm going to stop the video, and then you'll instantly see the work appear right there, because I've got to go do the row operations, and I don't want to spend 5-10 minutes doing that. Okay, so that's what I got there. And what does this tell me? Here's C1, here's C2, here's C3. It tells me, I know this is not row echelon form. I should put a 1 there to put it in row echelon form, 1/2, -1/2. But I don't really need to do that. I'm just seeing that C1 is bound because there is a pivot. C2 is bound and C3 is bound. So they're all bound, which means there's no dead weight there. So for part B, we say that this is going to be independent. Okay, we have no dead weight. Part A will ask, what does it ask? The question asks, does S span R3? Well, there's no dead weight and there's 3 of them, so the answer to that is yes, it does. For part C and D, those were conditioned on if you had a dependent set, so this is not applicable, not applicable. And for part E, it says, is S a basis? Well, yes, you have a minimal spanning set. The answer is yes on that. Okay, and it has 3, and we know the dimension of R3 is 3 as well. So that is problem number 25. Let's go ahead and do problem number 26. Oh, before we move on, I see on this one, you know, some teachers might say, oh, put that in a square matrix, put those in a square matrix by loading up the columns, which we have here, and check the determinant. Yes, the determinant will be non-zero, which means this 3 by 3 matrix is invertible, and then they can say, oh, well, then what you have is, yes, it does span R3. Well, that's not always going to work. You cannot always put your vectors into a nice square matrix, and that's why I'm showing you how to do the problems this way. Okay, it does work on some examples, but not on all of them. It would not work on problem number 26, and so the question is, does S span R4? Okay, so that's part A. Right away, we already know what the answer to part A is going to be. So let's put an A right here. That's part A. In order to span R4, you need at least 4 vectors, and I only have 3 vectors. So the answer to this, part A, is no. Part B asks if the set is independent. We'll come back to that. And C and D, well, that will be the dependency relationship, and that will be kicking out the dead weight. But we can already answer E. Question E says, is S a basis? Well, a basis has to have 4 elements for R4, so this one's a no as well. So let's check for independence. And see, I can't just throw those into a matrix. Well, I can, but I'm not going to have a square matrix, and I can't find the determinant of something like that. So what we're going to do is set up linear combination of these guys. So C1, 6, -3, 2, 0, plus C2, 1, 1, 1, 0, plus C3, 1, -8, -1, 0. This equals the 0 vector, which is 4 zeros there. Okay, so now I can write out those 4 equations. I'm going to skip that step this time. But if you wanted to write it out, it would be 6C1 plus C2 plus C3 equals 0. What I'm going to do with those 4 equations anyway is I'm going to throw them into an augmented matrix, which will look like this. 6, -3, 2, 0, 1, 1, 1, 0, 1, -8, -1, 0, and then the last one is 0, 0, 0, 0. Now don't tell me, oh, Joe, take the determinant of that, because well, the determinant would be 0, and that's not how we deal with all of our problems. In fact, we only had 3 vectors, so there's no way I'm going to be like saying, hey, let's take the determinant. That's just off the table. So what we want to do is we want to do row operations to see what happens with this matrix. So I'm going to go do the row operations and then I'll come right back. So when I went to go do the row operations, I realized that the 6, 1, 1, negative 3, 1, negative 8, 2, 1, negative 1, that happened to be in the last problem. So I'm pretty sure they did that on purpose, which made the row operations exactly the same as what I did in the other one, except there's another row of zeros. Well, then anyway, we have C1, C2, C3. Let's look at our pivots here. Here's a pivot, 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 which tells me what? Bound, bound, bound. There's no free agent. Therefore, this set of seeds is independent. Okay. Now, part C and part D, once again, I mean, this is what's been happening on these problems. Those are not applicable. There is no dependency relationship, and we're not going to kick out any dead weight. Now, you should know how to do this. What if I wanted to extend S so it becomes a basis for R4? Okay, so this is a follow-up question. Well, let's go ahead and call this one V1, V2, V3, V1, V2, V3, and we have to put how many more vectors in there for it to become a basis of R4? So it is an independent set, which means there's no dead weight in there, and that's why I decided to ask this question. But what do you notice about each of these 3 vectors? When you do linear combinations, and you may have noticed from this matrix, you never cover that last coordinate. So I'm going to go ahead and say, well, let's just extend this basis by putting 0, 0, 0, 1, sometimes that's called E4, into that set, and then this guy right here is the extended basis. Now we can check to see if this is correct by throwing these guys, checking for independence, you know, putting a plus C4 times this. I can actually see that it's going to work out, and I'm going to move on to the next problem. Okay, we wouldn't want to put 1, 0, 0, 0, because then I believe you would have a dependency relationship. So because all those vectors had 0 for the last coordinate, and you want to extend S so it becomes a basis for R4, we had to put the vector that had a 1 right there. Or whatever, you know, I mean, there couldn't be a 0 on that vector. Let's go ahead and continue to do these problems. Problem number 27, and once again, I'm taking them from the review. I'm taking them from 4.11. We have vector space R3, and we have 5 vectors. Wow, so we have 5 vectors there. And our question is, does S span V? Well, we don't know. We do see some dead weight. So this guy right here is dead weight. So that's going to answer question B, independent or dependent. It's actually going to be dependent because there's dead weight in there. We also know that the 4 vectors we have left over, one of them has to be another piece of dead weight. We don't know which one because you're in R3. So we know that this is a dependent set. We don't know if it spans R3. So what I want to do, even though I know this is dependent, is I want to set up linear combination of all 5 of those vectors. -3, 2. And going to set it equal to 0, 0, 0, the 0 vector of R3. I can write out the 3 equations. I don't want to do that. I want to go ahead and jump right to the augmented matrix. So when I jump to the augmented matrix, I get 10, -6, 5 in the first column, 3, -3, 2, and we continue. We have 0, 0, 0, 6, 4, -1, 7, 7, -2, and then we have the column of zeros there. Okay, so we want to do row operations on this. Now why am I doing this? Because I want to see if I have 3 bound variables in here when I'm done. If I have 3 bound variables, then yes, S will span R3. So that's what I'm checking for. Now I've already done the row operations. This time I've done them, okay, because I knew this problem was coming. And so what I got for the first row, I went ahead and put the 5 there. 5, 2, 0, -1, -2. Now it's not in row echelon form, but I didn't want to write a bunch of fractions. I'm just going to identify this as a pivot. And the other 2 rows I got were 0, 1, 0, -8, -11, and then 0. And then the last one was 3 zeros, 2 1s, and then we have the 0 there. So look what I have. I have a pivot, pivot, pivot. So look at this. This is C1, C2, C3, C4, C5. Bound, bound, C3 is free, freeloader, and we knew that because 0, 0, 0 is a freeloader, and then bound, and then I guess the other freeloader we can identify is the one with C5, which is that guy as well. So this is free as well. So this guy is dead weight. Okay. Now, let's answer some questions. Question A says, does S span V? Well, yes it does, because I have 3 vectors that are not dead weight, and we're in R3, so yes it does span R3, so yes. Is it independent or dependent? Well, we've established the fact that this set is dependent. Now, because of that, we have to write our dependency relationship. Our dependency relationship, well, there's a few ways we can do this. I'm going to go ahead and I'm going to solve this system. So I'm going to say that C5 is T because he's free. C4 is -T, and that comes from the 3rd row, where it says C4 plus C5 is 0. C3 is S. C2, well, I put -T in for C4, so that's going to be 8T minus 11T, which is -3T. So C2 minus 3T, bring the 3T to the other side, so C2 is 3T. And C1, you have a C, so this is, what is it going to be? I'm going to see here. I have 5 C1, so I actually can't do this one in my head. Maybe I couldn't do the other one in my head as well. I'm double checking the other one. Yeah, okay, so plus 2C2, so that's going to be plus 6T. minus C4, so that's going to be plus T, and then minus 2C5, so that's minus 2T. This equals 0. 5C1 equals, okay, so what do I have? I have 7 minus 2, which is 5T. I'm going to bring that to the other side. That's going to give me negative 5T. So C1 equals negative T. Woo! Got that done there. Okay, so what we're trying to do is get a dependency relationship. The dependency relationship, I'll let S equals 0. I'm not going to let both of them equal 0 and T equal 1. And when I have that, that's going to give me, I'll circle that in red, it's going to give me a negative 1 there, 3 there. We'll just say S is 0. It doesn't matter, that's the 0 vector. And then we have negative 1 there, and 1 there. And you can check to make sure these are correct. This is minus 10 plus 9, so that's negative 1, and then that's 0. Minus 6, which is then brings it to negative 7, plus 7 is 0. And you can do that with the other two components. So my dependency relationship is going to be negative 1. Let's call this V1, V2, V3, V4, V5. So what do I have? I have negative V1 plus 3V2. We won't write V3. And then we'll have minus V4 plus V5 plus 1V5 equals the 0 vector. 0, 0, 0. And we can write V5 as a linear combination of V1, V2, and V3. Now here's the funny part. We didn't have to do all this. And you're like, that's not funny, Joe. You just wasted our time. We didn't have to do all this because you can write another dependency relationship which says this. V3, which is the 0 vector, that equals 0 times V1 plus 0 times V2, or we could just write it like that. We just wrote V3 as a scalar multiple of another one. So this would be an acceptable answer instead of that. But you know, this was, we were really being high achievers on that one. Part D says, if you have a dependent set, and we do, then find an independent set of vectors that spans the same subspace of V as that spanned by S. So if you kick out all the dead weight, you just have V1, V2, and then V4. So that's a good rule of thumb to kick out all the dead weight. But the span of that is R3, so there are other possible answers that may be even more obvious, like I, J, and K. But you can't always do that when they ask you to kick out the dead weight, because you might have had this set not spanning R3. So this is probably a good way of doing this. And I believe the last question is S a basis? Is S a basis for R3? And we know the answer is no. It is not a basis because there's 5 elements in there and the basis has to be a minimal spanning set, so the answer is no. Now, V1, V2, V4, that set is a basis for R3, but that wasn't the question. It said, is S a basis? So that takes care of problem number 27. Let's go ahead and do one with polynomials. Number 28. Okay, first question, does S span V? Is it independent or dependent? So we could look here and see if we see any scalar multiples. I don't see scalar multiples. I think what I'm going to do is I'm going to go ahead and write out linear combinations of these guys. There's 4 of them here. So it's possible that those guys are a basis for P3. P3 being polynomials of degree 3 or less, real coefficients. So let's go ahead and write out linear combination. So this is 2x minus x cubed plus c2, 1 plus x squared plus c3 times 3 plus c4 times x. This equals the 0 vector of P3, which is just the polynomial 0. Okay, I'm going to go ahead and distribute some of these CIs. So this is 2c1x minus c1x cubed plus c2 plus c2x plus c2x squared plus 3c3 plus c4x equals 0. Let's go ahead and write out all of our equations. Our first equation, I'm going to circle all the things with x cubed in it, and that's the only one. On the right hand side it's 0, so it looks like I have negative c1 equals 0. I'm going to circle in another color all the x squared terms. So it looks like c2 equals 0. We know that c1 is 0 from the first one. I should have just written that down. I'm going to circle all the x's with a different color. So this one gives us 2c1 plus c2 plus c4 equals 0. But we know from the top equations, we know that c1 is 0 and c2 is 0, so this gives us c4 is 0. And we'll go ahead and circle the constants. This equation says c2 plus 3c3 is 0, and we know that c2 is 0, so c3 is also going to be 0. Now, if we had thrown this into an augmented matrix, for all of our CIs, we would have ended up getting bound. So what does that mean? That means this is an independent set. That means there's no dead weight. We know the dimension of P3 is 4. We have 4 vectors and none of them are dead weight. So those 4 vectors have to span V. So the answer to the first part of this is yes. Part B. Are these vectors independent or dependent? Well, we found out that because all the CIs are 0 and they're all bound, those vectors are independent. Which is good news for part C and part D. Those are not applicable. We're not finding a dependency relationship, and we're not kicking out dead weight. And for part E, are these 4 vectors, which are independent, and they span P3, are they a basis? And the answer to that question is yes. So we're going to do a few more of these problems. Maybe you're getting sick of seeing these problems. Maybe when I put up the problems, you should try to do them on your own. So here is number 29. So we'll do a few more of these, and then we'll find null space, column space, row space, Wronskians, and things like that. We have P4. So P4 has dimension what? What is the dimension of P4? This is dimension 5. Okay, this is polynomials of degree 4 or less. It has dimension 5. How many vectors do I have here? 1, 2, 3, 4. So you know what? And I'm going to put the answers up here. Does S span V? No, because there's only 4 vectors. So this is a no. Part B. Is it independent or dependent? Are these vectors independent or dependent? Well, just by looking at them, we don't know. So I'm going to go ahead and do what I did on the last problem, where I set up all linear combinations of them. So C1 times the first one, plus C2 times the second one, plus C3 times the third one, plus C4 times the fourth one. Okay, I'm going to distribute the CI's, so this is kind of like the last problem. C1 x to the fourth plus C1 x squared plus C1 plus C2 x squared plus C2x plus C2 plus C3x plus C3 plus C4x to the fourth plus 2C4x plus, running out of space here, 3C4, this equals 0. I'm going to go ahead and circle all my terms that have x to the fourth in them. That would be these two terms. I don't think I have any other x to the fourth. So this one tells me that C1 plus C4 equals 0. I'll circle all the terms that have x cubed in them. There are no terms that have x cubed in them. Okay, so I'm going to now circle all the terms that have x squared in them. That one right there. That one there. Any other x squareds? No, so this one's going to say C1 plus C2 equals 0. I'm going to circle all my x terms. There's one. There's one. There's one. So this says C2 plus C3 plus 2C4 equals 0. And then I'm going to go ahead and circle all my constants. So here's a C1, C2, C3, and 3C4. So we have C1 plus C2 plus C3 plus 3C4 equals 0. Oh man, okay, so I can try to go through this and try to solve this without an augmented matrix. I'm going to go ahead and write the augmented matrix. The augmented matrix for this is 1, 0, 0, 1, 0, 1, 1, 0, 0. Sounds like I'm in computer science class again. 0, 1, 1. And then this is a 2, and a 0, and then this is 1, 1, 1, 3, 0. Okay, there's the equal sign. And I went ahead and reduced this one. When I finished, I ended up getting 1, 1, 1, 3, 0. And then the next row was 0, 1, 1, 2, 0. So that looks like I wrote row 4, and then row 3. And then what I ended up getting was 0, 0, 1, 3, 0. And the last one was a whole row of zeros. Here's the equal sign. My variables are C1, C2, C3, C4. Let's look at our pivots. Here's a 1, here's a 1, here's a 1. So it looks like I have bound, 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 and C4 is free. He's the freeloader. So we know where the dead weight is. And so part B says, is it independent or dependent? Because I have a free variable, this one is dependent. Part C says we'll write a dependency relationship, which I'm going to do. Part D says if it's dependent, find an independent set of vectors that spans the same subspace of V as that spanned by S. So basically they want you to kick out the dead weight. Who was the dead weight here? This guy right here, x to the 4th plus 2x plus 3. He is dead weight. So if I just call this one V1, V2, V3, and this one is V4, then I'm going to go ahead and say, well, this, if I kicked out the dead weight, I would just have V1, V2, V3. And for part E, yes, I'm coming back to the relationship. I just want to put the relationship on hold here. Is S a basis? Well, S doesn't even span P4, so we knew off the bat that that was no. Now let's talk about relationships. Oh boy, here it goes. So, my dependency relationship. To do that, I have to actually solve this system a little more. Okay, so I'm going to say that C4 is T. Then we have C3 is, from the third row, we have C3 plus 3C4 is 0. C3 plus 3T is 0, so C3 is going to equal negative 3T. Okay, the next one I have, C2, I'll write this one out. Okay, so we'll circle those. This is the second row. C2 plus C3, so actually it's going to be minus 3T, plus 2C4, so plus 2T, this equals 0. C2 minus T equals 0, so it looks like C2 is going to equal T. Okay, let's move this up a little more. Our first row says C1 plus C2, that's plus T, plus C3, so that's minus 3T, plus 3C4, so that's plus 3T, this equals 0. Those 3T's cancel, and we have C1 equals negative T. I'm going to set T equal to whatever except 0, so I'll set it equal to 1, and I end up getting C1 is negative 1, C2 is 1, C3 is negative 3, and C4 is 1. Okay, so those are my C values. I can circle those in red. And what I'm going to do is I'm going to put those values right here. So this is negative 1, 1, negative 3, 1. And you can see, like, the x to the 4th is out of there. Look, negative 1, x to the 4th, and then here's a 1 x to the 4th. And so that's 0. And then let's look at the x squared terms. There's negative 1x squared plus 1x squared. No other x squared terms. So you can go through that and see that this linear combination of those 4 vectors does give you 0. Okay, so what does this mean? This means we can now write our dependency relationship. I've already labeled these vectors V1, V2, V3, V4. And so one way I can write the dependency relationship is going minus 1 V1, so minus V1, plus 1 V2, so plus V2, minus 3 V3, minus 3 V3, plus V4 gives me the 0 vector of P4, which is just 0. And so we have answered all 5 questions. Okay, a follow-up question for this one is, can you extend S so it becomes a basis for V. So extend S. So you've got to have, or maybe that's a bad question. Let's not call it S. I was trying to get another problem done here. Let's call this right here T. Okay, because T really is a basis for some subspace of P4. But can we extend that so it becomes a basis for all of P4? Now, how many elements do you have in here? You have 3 elements in there. So to extend that basis, you're going to have to add how many more elements? You're going to have to add 2 more elements. And what did we not see here on these ones? So this looks like an x squared. That's bugging me. So let me go ahead and circle these the way I wrote that. One thing we didn't see here is we never saw an x cubed, did we? That was one thing that was missing. So when we extend our basis, I'm going to go V1, V2, V3, and let's cross this out and say extend T, which happens to be those 3 seeds. And what I'm going to do is I have to add another vector. I'm going to consider the standard basis of P4, which is 1, x squared, x cubed, x to the 4th. And since I didn't see any x cubes in there, I'm going to put an x cubed there. Okay, now on these vectors, I do see an x to the 4th, and I do see an x squared, I do see an x, I do see a 1. So I think for this, and this is going to make some of you feel uncomfortable, it doesn't matter which other element I'm going to throw in there. I'm going to throw in an x to the 4th. And that there should be a basis for P4. Okay. So I'm sorry I confused you if I said extend S. We would never ask you to extend something that has dead weight to become a basis for something else, because how can you extend something that has dead weight in it? That means add elements to it in order to get a basis. You can't do that. So that's why I changed mine and say extend T, which is just V1, V2, V3. Those were the non-dead weight guys. And we extend it, so that's a basis for something, some subspace in P4, but it's not a basis for P4, so we extended it. Now, really, if you're a purist, what you want to do with all 5 of these vectors is to write them as a linear combination, set it equal to 0, and verify that there is no dead weight. If you end up getting dead weight on this one, then email me. But I'm pretty sure I'm correct on this, okay? Let's go ahead and do another problem. I think we've had enough of these kinds of problems. So what I'm going to do, I think I am moving. I have to move on, because if I don't move on, this is going to be an incredibly long review. And maybe I've done too many problems like the last kind. So what I'm going to look for now is this problem number 40, which is in 4.11. I'm seeing it. Yeah, so I'm not going to do all the problems I had planned to do just because we need to move on. So here's 4.11, problem number 40. And what does it ask? It asks us to find a basis and the dimension for what? Row space, column space, null space. So the first thing I want to do with this matrix is reduce it. I actually see that both rows, they're multiples of each other. So I could write the first row as like 1, 2, and then the second row as 0, 0. Okay. I'm going to identify the pivot right there. And let's go ahead and write a basis for row space of A. Okay, the row space is linear combinations of all rows of a matrix. Well, a basis of that, to find the basis, what you would do is reduce your matrix to row echelon form. And then the basis would be all the non-zero rows. So how many non-zero rows do I have here? Just one. It's going to be that top row, which is 1, 2. And so that's the answer to the first part. They asked me to find the dimension. I'm going to abbreviate row space even more, of RS, row space of A. Well, we've just found a basis, and how many are in the basis? Just one vector. So the dimension of row space is 1. And now I'm going to go ahead and find a basis for call space. That's the column space of your matrix. The column space is all the linear combination of your columns. Now, how do you find a basis for the call space? You reduce your matrix, you find all your pivots or your leading ones, and you don't take the columns of the reduced matrix, you go back and take the corresponding columns that line up to this one. So instead of going 1, 0, that would be incorrect. We would say -3, -6. And the dimension of call space of A, well, there's only one thing in the basis. It equals 1. There was a theorem that said the dimension of row space equals the dimension of call space. And we can see that that's true. That also equals the rank of your matrix. So the rank of the matrix, and I don't think they asked for the rank. I'm going to put it right here. The rank of A is 1. They also want you to find the basis for the null space. The null space would be gotten by putting zeros there and doing row operations. So let's just say the zeros would still be zeros there. Your variables, whatever you want them to be, I'm going to call them x and y. I have bound free y equals t. Okay, that's because he's free, and then x plus 2y equals 0. You're going to see that x equals -2t. Okay, so the null space looks like this: -2t, t. Factor out a t, this is -2, 1. That's linear combinations of just one seed. So a basis for the null space of A is basically just this one vector, -2, 1. -2, 1. So that's that answer. And then they ask for the dimension of the null space of A. The dimension of the null space is also 1. Okay, now the dimension of the null space is not always going to equal the dimension of the call space and row space. That just happens to be 1 on this example. The dimension of the null space, we're done with the problem, by the way. That has another word which you should know for the test: the nullity of a matrix. The nullity is the dimension of the null space. It's 1. The rank nullity theorem says if you go rank plus nullity, so 1 plus 1 is 2, that gives you the number of columns of your matrix. Another way of saying rank nullity theorem is the rank represents the bound variables, and the nullity represents the free variables. They're saying the bound variables plus the free variables equals the number of variables. And so we are done with problem 40, and we're looking to see what we can do now. Let's go ahead and do problem number 41. We'll do another problem that is like problem 40, where we are to find a basis and dimension for the row space, call space, null space, and I'll even verify the rank nullity theorem on these problems. Okay. This is indeed the problem that I want to do. So what do I have here? I'm going to go ahead and reduce this matrix. That's the first thing that we do when they ask for all those things. Now this matrix can become 1, -6, -2, 0. Then I have 0, 21, 7, 5. And then the last row is just all zeros. Now, is this matrix in row echelon form? No. I didn't want to put it in row echelon form because I didn't want to put a 1 there, because if I had put a 1 there, I would have to put 7 over 21, which would be 1/3 there, and then 5 over 21, which would look like a mess. So here is the matrix. It's reduced. Let's go ahead and do the questions that they asked us to do. Basis for row space of A. I'll identify the pivots. So that's why I always say pivots, because this time the 21 is not a leading 1, it's a leading 21. And the basis for the row space is just going to be 2 elements. It's going to be those 2 rows there. So I'm going to go ahead and write that out here. So we have 1, -6, -2, 0. And this is 0, 21, 7, and 5. I bet if you look at the answers in your book, they'll write this one as 0, and they'll divide everything, you know, they'll put this in row echelon form. So this would be a 1 here, this would be a 1/3 there, and this would be a 5 over 21. Okay, well, it doesn't matter if you scale these things down after you write out your basis. You can scale it, you know, so it has fractions, so it doesn't have fractions. So that is the basis of the row space. The dimension of the row space happens to be, well, just 2. Let's look at the basis for the call space of A. So you kind of start off the same way. You reduce your matrix, and then you look at the pivots, but you go back to the original matrix, and you grab on to those columns. And so the basis for call space would be -1, 3, 7, and then we have 6, 3, 21. The dimension of the call space of A is also 2, and we knew those are going to be the same, okay, because the theorem says dimension of row space equals dimension of call space. The next thing I'm going to do is I'm going to find the null space. The null space I get by putting zeros along this column, and it's AX equals 0. And so you solve that homogeneous linear system. And what I have here is I have to come up with some variables, and you know me, I'm going to come up with X, Y, Z, W. X and Y are both bound. Z is free, and so is W. So I'm going to say W equals T and Z equals S. So watch what happens here, and I'm going to show you a little trick that you can do. Okay, but right now we don't know what's about to happen. Second row gives us 21y plus 7z plus 5w equals 0. 21y plus 7s, camera cut out there, plus 5t equals 0. 21y equals negative 7s minus 5t. And here is the deal. I mean, if I go ahead and divide by 21, I'm going to have some issues here. Now, we can continue to do it this way. There's nothing wrong with that. So then I would end up getting y equals negative 7 over 21s minus 5 over 21t. Now, of course, 7 over 21 is going to become like 1/3. So here is the trick that you can do. Let's try this again. This time I'm going to let w equal 21t. This is just a different parameterization. This is a matter of style because I don't want to work with fractions. I'm going to let z equal, because I can see this is 1/3, I'm going to let z equal 3s. If you don't like this, if you think this is dangerous, then go back to this and continue, and you still have the first equation to do. So I'm going to go ahead and write out this equation now. I have 21y plus 7z, so that's 21s, and then I have plus 5t, so this is going to be plus, I'm going to go 5 times 21t, this equals 0. So the 21s can be divided out, and I have y plus s plus 5t equals 0. And so y equals negative s minus 5t. Okay, so that looks a little better. Now, the payoff is there's a 21 there, and that's kind of crappy. Let's go ahead and finish this up now. I need a little more space on the paper. Oh, before I do that, I better write out this top equation. It says x minus 6y minus 2z plus 0w equals 0. Okay, so going up here, and so I'm going to say x minus 6y minus 2z plus 0 times w. Good thing, because I didn't want to write that 21 there. This equals 0. Okay, we'll just do a little algebra here. This is 6s plus 30t. That's pretty bloated. And oh, wow. I'm putting an equal sign. Don't know why. It's gone. No one even knows. There's a plus sign. Oh, maybe people will know. So plus 6s. And then hopefully I didn't say equal when I wrote it. Minus 6s equals 0. Oh, look at that. Those guys are out of there. So it looks like x equals negative 30t. So what do we have for this? For our null space, it's going to look like this, negative 30t, comma, minus s minus 5t, and then 3s 21t. I'm going to splactor it. So when I splactor it, I'll just, oh, I just wrote the t. That's going to be all right. This is negative 30, comma, negative 5, comma, there's no t there, so 0, comma, 21. Then we have plus s. Then we have 0, negative 1, 3, and 0. So here's a matrix. They asked me to find the null space of this matrix. And I'm almost done doing that. What I'm going to do, well, actually they asked me to find the basis of the null space of A. And so look, I have a linear combination of two seeds. It's going to look like this. It's going to look like those two guys there. So I'm going to write them out here. Negative 30, negative 5, 0, 21, and then the other one is 0, negative 1, 3, 0. And so we have, this is our basis. The dimension of the null space of A happens to be 2. Now I know what you're thinking. You're thinking, Joe, that is the dimension of these guys here. Now that doesn't always happen. Dimension of the null space is always your free variables, and the dimension of the row space or call space happens to be your bound variables. And in the last problem, there was one bound and one free, and in this problem, there were two bounds and two frees. But if you've done your homework, you'll see that the rank does not always equal the nullity. So what does that mean? In this example, you have the rank of A happen to be your bound variables. There's two of them. And the nullity of A is also 2. That's your free variables, and that adds up to 4. So why in your review do they always make them the same? Well, I don't know. Maybe number 42, they are different. But right now, I want to move my attentions to a problem that I'm going to use off of this problem. So we're done with this problem. We found a basis and dimension for the row space, column space, and null space. So now what I have here is I have this matrix A. This is the one we just did, where the null space, yeah, this is exactly the same problem, is that. So here's the null space, and then now I'm going to let something new happen. Let a column vector equal negative 1, 1, 1. Now I'm telling you a particular solution to AX equals B is this, negative 1, 0, negative 1, 1. Okay? So that means if I went A times this written as a column vector, I'd get negative 1, 1, 1. Write the general solution. Okay, so you're going to get one like this on your test because this is so important to differential equations. Your general solution will always be the homogeneous part, and they put a C there, and we'll talk about that when we hit differential equations. I think this is a little less confusing. The homogeneous part plus a particular solution. This guy right here, the homogeneous part, I don't know where I can make it. This is really the null space. And so there's a reason why in this problem I said, here's the null space. So what I'm going to do when I write out my solution to this system, because this is what I'm trying to solve. I'm trying to solve this. I'm going to write the null space out, but as a linear combination. I'm going to go C1 times negative 30, negative 5, 0, 21, plus C2. And we have 0, negative 1, 3, 0. So that right there happens to be x sub h. Particular solution is this guy right here. So I'm going to go plus negative 1, 0, negative 1, 1. And so there's the answer. So if you get something like this on the test, you shouldn't have to do any row operations. You just put the homogeneous part, that's the null space there, plus the particular solution. And that solves AX equals B. Okay, let's go ahead and do another problem here. For problem number 42, I just want to find the rank and nullity on this. Okay, so I know they asked for some other things, but I did not feel good about the other problems where the bounds and frees were always the same. So find rank and nullity. Okay, so that's what we'll do here. So how do I find the rank and nullity of this matrix? I reduce this matrix to row echelon form. And when you reduce this matrix to row echelon form, I'm not going to reduce it to row echelon form actually, because I don't want to have lots of fractions in it. So what I ended up getting is 2, and then we have -5, and -10. And then the next row I'm just going to keep it like this. So 0, 10, 13, and then 0, 0, 1, and then 0, 0, 0. Okay, so this is not in row echelon form because I didn't want to scale this down. So you ended up getting lots of fractions. Okay, so that's what I ended up getting. Now, I mean, maybe it will help by putting some zeros here. Okay, so let's find the null space of this. Well, if you're going to find the null space of this and your variables are like x, y, and z, you'll find that all your variables are bound, which means x equals 0, y equals 0, z equals 0. So the null space of this matrix happens to be, the null space is 0, 0, 0. We're not going to ask you to find the basis for that because 0, 0, 0 itself is not a basis, so it would actually be the empty set, but we're not going to get into that. The dimension of the null space is 0. So that's also called the nullity. So the nullity of A is 0. Now the rank of A happens to be 3. That's the number of bound variables. Nullity of A is the number of free variables, and you take these guys and you add them together, you end up getting the number of variables or the number of columns of your matrix. Okay. So we found the rank and the nullity, and if we found the call space and the row space, I'm not going to write them down, but a basis for the row space would be these 3 rows there. Okay, so that would be the basis. And a basis for the call space would be these 3 columns. And those guys all have dimension 3, not dimension 0. So that takes care of problem 42. I went in your book somewhere and I found this problem somewhere in your book. Find the Wronskian of this matrix. So we have a few other problems that I'll go over and then we'll stop this review. How do you find the Wronskian of a matrix? You go ahead and you take these functions here, sine x and cosine x, and you make them be the top row of a matrix. And then you take derivatives until you get a square matrix. So the derivative of the sine is the cosine, and the derivative of the cosine is negative sine, and you take the determinant of that. So the determinant AD minus BC, this is negative sine squared x, and then minus BC, so minus cosine squared x. I'll factor out a -1. So really what we have here is sine squared plus cosine squared is 1, so this is -1. That's the Wronskian. So on the test, if I ask you to compute the Wronskian, that's what you would do. What does the Wronskian show about dependent independent? Well, because the Wronskian is -1, which does not, I should have put an interval here, so I'll put the interval from -infinity to infinity. Since it is non-zero for at least one x in that interval, so this does not equal 0, for one x in that interval, then that shows that these two functions here, sine x and the cosine x, are independent. So f1, f2 are independent. So that's the only thing the Wronskian can show is independence. The Wronskian can never show that things are dependent. So if the Wronskian was just exactly 0, then the Wronskian would be inconclusive about dependence and dependence. Let's go ahead and I couldn't find any problems like this in the review in 4.11, so I went to 4.7, and hopefully I picked out something that wasn't in our homework. You have P2, you have an ordered basis for P2, which has 3 elements. Here's a polynomial in P2, and they want you to find the component vector of P relative to B. And then there's the notation. So what am I going to do? I'm going to write P of x as a linear combination of those basis elements. So -4x squared plus 2x plus 6 equals C1, and we have x squared plus x plus C2, 2 plus 2x, and then we have C3, we have 1 right there. So that's what we're supposed to do. Now some of you might think that these two vectors are scalar multiples of each other, because you can factor out a 2 and you have a 1 plus x, and then you can factor out an x and you have an x plus 1 or a 1 plus x. Well, that's not a scalar multiple. I mean, they are multiples of each other in terms of polynomials, but it's the scalar multiples, like you could say, does this one equal 2 times that one? No. And so it has to be a scalar multiple, not just a polynomial multiple of the other one. Let's go ahead and distribute the CI. So I have -4x squared plus 2x plus 6 equals C1x squared plus C1x plus 2C2 plus 2C2x plus C3. I'm going to go ahead and circle all my x squared terms. And it looks like I get -4 equals C1. Circle all my x terms. And that one gives me 2 equals C1 plus 2C2. And then I'm going to circle all my constants. That gives me a third equation, which says 6 equals 2C2 plus C3. Is it true that I can throw this in an augmented matrix? Absolutely, but you know what? I can use that to figure out what C2 is. So what do I have? I have 2 equals -4 plus 2 C2. So 6 equals 2C2, C2 equals 3. And now I can get this one, because now I know what C2 is. So I have 6 equals 6 plus C3. C3 equals 0. Can that happen? Well, it just did. So C1 is -4, C2 is 3, and C3 is 0. This component vector can either be written as a column vector or just an ordered triple here, and it's just your C1, comma, C2, comma, C3, but what values they are. So this is -4, comma, 3, comma, 0. So there's your answer. That's problem number 8. Okay, so here's an example where you are looking at R2 and you have an ordered basis B and an ordered basis C. Find this change of basis matrix. Now the quick way of doing this problem is to load up the columns of a matrix with the vectors from C without switching their order. So this is 7, 3, 4, 2. And then we put the vectors of ordered basis B over here. So this is 1, 2, and then 3, 4. What do you do with this matrix? You do row operations until you end up getting the identity there. When you do that, you'll end up getting the answer right here. That's called your change of basis matrix. Your book does not show this method. Your book says it's the component vector of this guy with respect to C and the component vector of the second one with respect to C, and that's how they do it. But this way will work on all the problems that we have to do, because we'll always be in Rn in this class when we find change of basis. So how am I going to do this? I'm going to go ahead and I'm going to multiply. I will actually work out the work here. Multiply the first row by 3 and the second row by -7. So this gives me 21, 12, 3, 9. The bottom row is -21, -14, -14, and -28. So when I do that, I end up having 7, 4, 1, 3. This one gives me 0. That's what I want. And then right here is -2. This guy right here is -11. Starting to get a little yucky here. And then this is -19. So that's what we have. So now what I'm going to do is I'm going to multiply row 2. I'm using this as a pivot to put a 0 there. I'll multiply row 2 by 2 and add it to row 1. So this is 0, -4, -22, and -38. Ugh. Okay, well that's alright. I'll just go with this. So what I'm going to end up getting here is 7, because 0 plus 7, and then we have the 0 which we want it. This is going to give me -21, and -38 plus 3 is going to be -35. All those numbers in row 1 are divisible by 7. That's happy news there. Row 2, well, I guess I'll go ahead and just write the positive parts of those, multiply that by -1, so we have that. So I'll multiply row 1 by 1/7 and multiply row 2 by 1/2. So I end up for row 1 getting a 1, 0, -3, -5, and for row 2 I'll end up getting 0, 1, 11 over 2, and 19 over 2. And so that's what I'll end up getting. Our final answer to this, I'll use another piece of paper right here, is actually going to be this right here. Here's your change of basis matrix, and it looks like this. So -3, -5, 11 halves, 19 halves. Okay, so here's a follow-up question. Okay, so here's a follow-up question, example. Suppose you have a vector v, which is written in terms of world v. Okay, so this is the component vector. And let's say this vector is like 2, 4. Use your change of basis matrix to find the component vector relative to world C. So that's our follow-up question on this. So let's see if we can do that. This component vector right here is actually equal to the change of basis matrix multiplied by the component vector of V relative to B. It looks more complicated than it really is. All I'm going to do is write this. Okay, the camera actually ran out of battery juice there, so let's see what we were doing. -3, -5, 11 halves, 19/2. I'm going to go ahead and multiply that by this guy right here, and I'm going to write this as a column vector, 2, 4. So when I do the multiplication, see what I end up getting. -6 minus 20. And on the bottom, I end up getting 11 because the 2's canceled. Okay, good. And then 19 halves times 4. So that's 38 plus 38. So this gives me -26. And then over here is going to be 49. So hopefully that's what I got. Now this is an acceptable answer, or you can write it like this. You can write it as -26, 49. Now we would never say that equals just vector v. We would say it equals this guy right here. Okay, the component vector. Okay, so I believe we have 2 more problems. We'll finish these 2 problems and we'll be done with the review. The review may have run over 90 minutes, but usually people want to see problems worked out by the teacher. So I'm not doing any new material. All I'm doing is stuff that we've done in the lectures. Okay, our vector space is B2. The inner product of 2 polynomials. This is the standard one where you multiply coefficients of the x squareds and add that to the multiplication of the coefficients of the x and then add it to CF. So it's a standard inner product. It's kind of like the dot product, but it got generalized. You've got these 2 vectors here, these 2 polynomials in P2, and they're asking us to find the angle between P and Q round to the nearest degree. Okay, so the formula that has an angle in it looks like this. The inner product of P and Q, this equals length P times length Q times the cosine theta. So the inner product, we've got to find a few things, and we'll find them over here off to the side. So this is where I'll do some of the work over here. It's the inner product of P, Q. So I'm going to use this rule for the inner product. So AD. So I take the coefficient in front of the x squared up on P, and the coefficient in front of the x squared there is 0. 0 times 1 plus 1 times -2 plus, and then we have 1 times 3. So you do all that calculation, you end up getting 1. Okay, I want to find the length of P. This is going to be the square root of the inner product of P with itself. So this is the square root. So I have 0 squared plus 1 squared plus 1 squared, so this is square root 2. The length of Q is going to be the same thing, well, except there would be Q's there. And so I'm going to say the square root of 1 plus 4 plus 9. So this is the square root of 14. So I'm going to plug this information into this formula. Inner product of P and Q is 1. Length of P is root 2. Length of Q is root 14 cosine theta. Divide both sides by root 2 root 14. You get cosine theta equals 1 over the square root of, I'll just write this as 28. You can do that if you want, because I'm going to be entering this into the calculator. It's the first time I had to use my calculator for a while. During this review, I don't think I used my calculator at all. 1 divided by the square root of 28. I believe it's in degree mode. I end up getting 79.1. It says round to the nearest degree. So theta is approximately 79 degrees. Let's go ahead and do our last problem. Is this an orthogonal set? If yes, find a corresponding orthonormal set. Now on the test, I'm going to write it all out. I'm not going to try to abbreviate like this. So the first thing I want to do is, well, first I hope that the answer is no, because then I don't have to do that part. I'm going to find the dot product between those. So when the inner product is not given, like in R5, then it's the dot product. And that's going to be, look, it's going to be 0 plus 0 plus 0 plus 0 plus 0. So that's 0. Okay, the dot product between these guys right here would be 0 plus 2 plus 0 minus 2 plus 0. So that one's 0. Then here we have 1, and then that's a 0. And then we have plus 3. So now we're at 4, and that's 0 minus 4. So if you have zeros for all your dot products when you go pairwise within all the vectors in your set, then the answer is yes, this is an orthogonal set. An orthonormal set is a set where it's orthogonal and each vector has length 1. So we've got a, we have a yes here, so we have to find a corresponding orthonormal set. Let's do that. I'm going to divide this vector by its length. The length of this vector is the dot product of this vector in itself and then the square root of that. So 1 plus 0 plus 1 plus 0 plus 1. So that's going to be the square root of 3. So the first one's going to be 1 over root 3. 1, 0, 1, 0, 1. This one has length 2. So the length root 2. 1 over root 2. And then we have 0, 1, 0, 1, 0. And then this one, let's see, if I dot this with itself, I have 16, plus 4 is 20, plus 9 is 29, plus 4, 33, plus 1 is 34, so then we take the square root of that. This is 1 over root 34, 1, 2, 3, negative 2, negative 4. There is the set. Okay, so the deal is work your homework. This test is coming and you'll see similar kinds of problems on your exam. Have a good day.